that today's guest and star is Jared, whose last name I think is Poche. I'm not sure.
Poche.
Poche. Okay, Jared Poche, and Jared is going to talk about performance tuning. Every millisecond counts, and it's. I'm really looking forward. I love it. I love the, you hear stories about people who they tune a stored procedure from 5 minutes to 1 second. Jared is going to talk about tuning from 1.5 millisecond to 1 millisecond and stuff like that. So I'm really looking forward to it. Welcome, Jared. The stage is yours. By the way, if you have questions during the talk, then write them in the chat and I will interrupt Jared so we don't get everyone speaking at the same time with low risk going in the background and so on. Welcome, Jared.
Well, thank you very much. I appreciate the opportunity to speak to you this morning, and I hope all of you are having a good day in Europe, or the majority of you, I'm sure, are. So this talk is Every Millisecond Counts. This is a case study that came from the work I do during the day with my company ChannelAdvisor, which works in the e-commerce business. So a bit about me first. I've been a database engineer for ChannelAdvisor for about 5 years. I have a really good team of database engineers and administrators where I work. I have my Twitter handle if you want to follow me. I also have my SQLJared.com is where I've been blogging for the last couple of years. I am also a 10-year veteran of Microsoft CSS. I've been a SQL Saturday speaker at a number of events in the region, and I've spoken at Virtual Pass this year and last year. This actually was the talk that I gave at Virtual Pass this year, and this covers work that I started on around the time the pandemic started and going through the next several months, releasing multiple individual changes in as we were tuning this stored procedure so that we could see each change in isolation and measure how it actually affected things. So to set expectations, this is an intermediate to advanced level session. What made me think that this was something that would make a good session is that it very much was not standard query tuning. It wasn't easy stuff. It wasn't just we were missing an index or we had table scans that we needed to address in our stored procedures. This went a lot farther.
Do you think you're sharing the screen? Because you're not.
Oh no. Hold on a second. Hold on.
No problem.
Wait a second.
There we go. Perfect.
Actually, I don't want to share that window. I want to share my entire screen. There we go. Because I'm going to be changing in and out of Management Studio for some of the examples later. So my apologies. Should I restart?
No, I think we're good. I mean, it's if you could go back to the slide with the URL.
Okay. SQL Jared is the URL for my blog. My SQL Jared is also my Twitter handle. So if you have any questions as a result of this and you want to follow up, here's where you would go with that. My apologies for the snafu. You're seeing everything fine now?
Yep, looks good.
Okay. The goals for this was just kind of to show the attention to detail we had to have to see the opportunities on this one. I hope that you will learn a couple new coding techniques, and I hope that you will think about how the design and flow of your application, how that will affect the database, because one of the biggest gains we had of this is really came from understanding how the application worked and how our users interacted with it. So a little bit of foundation. A number of topics come up during this talk, and I want to go ahead and introduce each one of them first quickly. So this is all about troubleshooting or performance tuning one stored procedure, and this procedure is an upsert procedure, which is we're trying to update a number of records in the underlying table, and some of those records might not exist, and so we will try to update the record, and if not all of the records exist, we run an insert statement afterwards to insert the record in case it didn't exist. I came across a blog post from Aaron Bertrand sometime after I had done this work that seemed to have like a lot of overlap and was talking about upsert procedures and a number of optimizations for how to get them to work better. So I did actually include a link at the end of the slide deck for his blog post, because I thought that was a really good post on the topic that covers a lot of cases. So table variables. Table variables get kind of maligned, but we use them rather heavily. The main thing that people will bring up when dealing with table variables as opposed to using temp tables is that temp tables have statistics and table variables do not. So the optimizer, when it's dealing with a table variable, unless you are dealing with SQL 2019 or later and are using intelligent query processing, the SQL Server optimizer assumes a table variable only has one row in it. Well, this can sometimes lead to it making bad decisions because it doesn't understand the cardinality exactly. Table variables are also objects that are stored in Tempdb like temp tables, but the main issue with table variables is people tend to prefer table variables because they do have statistics, which can lead to better execution plans. We use them heavily in part because we like using table valued parameters. So TVPs allow us to pass in a table variable as an input parameter to a stored procedure. So we use this and allows us to pass in essentially rows of information, and we can then update multiple rows inside our underlying table based off of that. Using TVPs allow us to do processing in batches rather than having to make 50 calls to a given stored procedure to update 50 rows in the underlying table. Instead, we can use a TVP, call that stored procedure once, and update the same 50 rows. This saves us a ton of time, not only in the database engine, but it saves us a lot of time in round trips from the application to the SQL Server. And not having multiple threads trying to insert in the same table at the same time means we have a lot less contention within that table. But we are not just using table variables and TVPs. We're using memory optimized table variables and memory optimized TVPs basically everywhere. These still have the one caveat of not having statistics, but now we're not even creating the object in Tempdb anymore. We're just storing the information in memory. This gives us an extra layer of optimization, as we don't have the typical Tempdb contention that you can have when you're creating objects very quickly. I bring up a tablespoon operator in a point or two as I'm looking at the execution plans, because it was something that did grab my attention. A tablespoon operator is typically a place where SQL Server is taking an internal result set from the middle of the execution plan and saving that off so it can refer to it later. Typically, if it needs to take a given result set and use it multiple times later on. If I see those, that does tend to grab my attention. They tend to be relatively expensive operators to begin with, but it also makes me wonder about the complexity of a given query. Is if we're in a place where I can see that we're using tablespools a lot, is there a way I can maybe rewrite this statement a bit and try to simplify it some? Are we making things more complicated than they have to be? Also, we use indexed views. Of course, you can have a view, and a view is basically just a logical construct that doesn't store any data, but just kind of allows you to access information from a specific query. Well, we do have an indexed view in this case. That is one key point of what we optimized. And an indexed view, you are actually going to be storing the physical data that's defined by that view. And so anytime you update any of the underlying tables, the view also has to be updated in the same way that SQL Server will, when you update a table, it has to update all of its indexes. Well, it also would have to update any related indexed views, and that's an additional overhead that can be noticeable and was noticeable in this case. One last topic that comes up is the Halloween problem and Halloween protections. And it's kind of involved, and I'll go into it a bit later on, but the Halloween problem is a problem that comes up with database management systems in general, not just SQL Server. This was something that was originally identified in the late 1970s by, I think, IBM engineers that were working on a database of theirs. So the Halloween problem occurs when something like an update statement could possibly update a given row multiple times. This is to be avoided in SQL Server puts protections into place to prevent the Halloween problem. So it prevents us from potentially updating a given row multiple times. The trade-off is that the protections tend to not be great for our performance. All right, so this is a case study about work I've done working for ChannelAdvisor. Among other things, we do inventory management, and part of that is keeping track of the quantity of items that are available for sale. So this is an e-commerce platform. This stored procedure is trying to update multiple rows in the underlying table. So in our quantity table, even if when we're updating quantity for a given item, that item might have multiple rows indicating that it has quantity in different distribution centers. So we're updating multiple rows for a single item by passing in a memory optimized TVP with the quantity that we want to be set on each of those distribution centers. So the updates, the behavior is completely customer driven, and some of it is going to be as they tell us about new invoices that have been completed, new purchases, things like that. But also they'll upload details telling us that they've just gotten in, 10 more of these particular shoes, and we have to update the database. This stored procedure was taking 3.1 milliseconds on average when we started working on it. And all the numbers that I'll be putting out here come from Query Store. So we were running this 3.1. This was taking 3.1 milliseconds per execution on average, and you might wonder why we would bother trying to tune something that's running that quickly. And the reason was we were running this almost 300 million times a day when I started working on this, and that's over dozens of SQL servers and hundreds of databases running the same schema. Different sets of data, different information for different customers, but essentially the same statements and the same stored procedure running on all of them against the same schema. So the gist of my goal here was to try and reduce the runtime of this stored procedure by 1 millisecond if I could. The thought was any benefit we get here is going to be multiplied so many times that it would be a significant difference. So what does the procedure do? And forgive me, I'll be working through this. I'll be providing some information, but we're going to be using anonymized execution plans. I can't show you the actual code, but I can give you the gist of what the procedure does. First, it runs a pretty simple and pretty fast query to populate it to a few variables. That's not really an issue. It doesn't take any significant amount of time. Then we check for item listings. And to describe this as best I can, for the item listings, let's say you have 20 of a given item for sale. And let's say that you've got 5 of them that you've already got posted on some platform. Let's say you've got 5 up for sale on eBay. So what this does at this point is we go and check for any outstanding items that are available for sale or anything that is yet to be shipped, things of that nature, so that we can subtract it back out of our totals later on. If you tell me you have 20 of a given item, but you have 5 of them for sale, you really only have 15 that are available. So we have another query that does some of that math for us and checks for item listings. Then we perform the update against the main table here. This statement is taking 80% of our runtime when we start off. So the logic there is a little complicated, but we know at some point if we're going to really try to improve the performance here, we're going to have to get something out of that update statement. And then we do an insert where we try to insert any missing rows. So if our TVP passed in, say, 5 rows in the TVP, so we're trying to update 5 rows in the underlying table. Well, if I only update 3 rows, then it's probably because the other 2 rows don't exist. So now we're going to run an insert statement to insert the missing rows. I did find quickly that this insert statement was causing us to trigger and do operations on another table. So that got my attention as well. So here is part of the anonymized execution plan. And let me zoom into this real quick. So there's a lot going on here, and like I said, there's not I said this wasn't exactly typical troubleshooting, and one of the things I said specifically is there weren't any table scans. And if you're looking at this, you might see that I appear to be wrong. But what this operation here is an index scan, but it's a scan against one of the memory optimized tables. So this is table variables, and you can see here our row counts are kind of funny here too. And basically all these operations, we're getting one of one or one of two. We're only touching a row or two. But I can see that these two scan operators, I can tell you that both of these are going against memory optimized TVPs. So they're not really a problem. We also have a index seek against another memory optimized table variable, also not a problem. And we've got a lot of scalar operators. We've got some filters, but we've got a very small row count. So there's very few rows going through our typical execution of this. But there's something else that really got my attention here. So this is our base table that we're querying against, object 7. So we've got an index seek against it here, and we have another index seek against that object here, and a key lookup against that object here. So it really got my attention that we were hitting the underlying table 3 times to try and get the information. Now, it is not unusual for me to look at a key lookup and to try and see what we can do to get rid of the key lookup. But I also wondered why we had 2 index seeks here. So that started to get my attention. So this is all kind of this is just the start of our select portion of our update statement here. So we query all of this, we join it together, and this is where we're actually changing the data. So here we have our clustered index update. So we've joined all of our data together, we've sorted it, we've done some scalars, and then we do our clustered index update. We should be largely done at this point. And it got my attention, it really got my attention that we have a table spool, eager spool after the clustered index update. Now, when you're going to spool results, you're spooling them up so that you can use them typically somewhere else afterwards. And it's not that unusual for you to see a table spool of some kind and then see that we're updating indexes and updating some of the other indexes on the table. But this one got my attention because there was a lot of work going on here. So this middle line, so we're reading our table spool and we're doing a clustered index seek. Okay, fine. We're doing a sort operation that's kind of expensive. We're doing another sort operation that's kind of expensive. And then we're doing a second clustered index update. And I must admit, this took me a minute to figure out what exactly was going on. But what's going on is we're updating an indexed view. That's why we're updating object 20, not object 7 again. So this took me a couple of minutes to piece together. So we're spooling up our results after we've updated our main table so that we can get that information together, aggregate it, and update the indexed view that's based on this table. So this was kind of the first thing I saw that really gave me an idea of where I might be able to optimize this. I said, okay, we've got these spool operations and all of these sort operations, and I think I looked at this and found that that middle line actually was something like 70% of the cost of our execution plan. Now, cost numbers are always estimates. This cannot be forgotten. Even in an actual execution plan, the cost numbers are estimates that SQL used kind of on the front end to decide what plan to use. But that's a lot of cost. And another thing that gets my attention that I want to point out is that our clustered index update, the actual update operator against the table, is only 22% of the cost of the table. And from my experience, if you've got a DML statement, the most expensive thing is typically going to be the operator that's actually doing the write. For it to be 22% is really low. Typically, I would expect this to be 70 or 80% of a well-tuned statement. So it says to me there's an awful lot of other things going on if the update is actually this small an amount of the cost. So I was thinking to myself, well, do we really need that indexed view? We were probably going to need the view, but do we really need it to be indexed? Because if we didn't have to update that, that would be an awful lot less effort. So that was the first idea I had in trying to see how we could tune this stored procedure. The second one is this: how much of the time do we do unnecessary insert statements? if we're passing in 5 rows in our TVP, I'm expecting most of the time, possibly the vast majority of the time, we're actually updating 5 records. And that our insert statement, which has a where not exists clause on it, and that our insert statement is probably redundant. It's probably unnecessary the vast majority of the time. But we're running the insert statement every time, whether we need it or not. Is there some way we can skip that? In part, if we can skip running that insert statement, we can skip running the trigger. The thing I didn't realize before I started this is that if you run an insert statement and it inserts 0 rows, you still run the trigger. You still run the trigger. You're still going to, build the little space for the trigger to operate in. You're going to create the inserted table. You're going to create the deleted table. You're going to go in, you're going to context switch over there, and you're going to run its statements, and you're going to do nothing. So if we could skip all that, that seems like that would be a nice benefit as well. The third idea I thought was about table variables itself. So this stored procedure has a TVP that gets passed in. We use a couple of table variables internally within the table, all memory optimized, yes. But I had wondered about the idea of cardinality and the fact that the optimizer is not going to have any estimates. It's going to think everything is going to be 1 row. So my thought was, well, what if we changed it over to using temp tables? If we change it to using temp tables and we have statistics, is the optimizer maybe going to make create a better plan? It's going to come up with a better optimization for the stored procedure because it has that statistics information available. And the fourth idea was going back and looking at the update statement. Like I said, it was a little bit involved, but there are key lookups. There are multiple references to the underlying table, and we definitely need to spend some time there and see what we can get out of that. Any questions so far?
Nothing in the chat. So
okay.
People, if you do have questions, just feel free. Don't be shy.
All right, I'm gonna take a break for a moment and do a little bit of setup. So I have, along with this, I have a GitHub where all of my examples and all of my slides are available. So if you want to refer to that, you can, and you can take a look at my code examples later on. I want to restore the database from backup just to put us back at a starting point. Now, I'm going to create a memory optimized file group. And I'm just checking to see if my file group exists, and if not, we're going to create it. And the same thing for, I'm going to create a file to go into our memory optimized file group. And I'm going to create a couple of table types. I'm creating types. They are table types. I'm checking to see if they already exist. They are memory optimized. This one has 3 columns and an index. The second one has a few more columns. This is all I'm using the AdventureWorks 2014 database for my examples. Hold a second. Okay, I must have had something highlighted when I ran that. Okay, we're fine now. And
I have a question from Alexander, if it's okay.
Go right ahead.
Is there any huge difference in performance point of view between table variables and user table types?
Between table variables and user table types, table variables are largely, I would think of them more as temp tables. So is there a big difference? In general, I would say no. The biggest thing would be when you're creating a table variable, you're going to be creating it in Tempdb. And if you experience if you experience Tempdb contention, then when you're creating a table variable, you would see it with table variables just like you would if you create an awful lot of temp tables in your normal operations. So outside of that, I would say they're a lot like temp tables, and I would liken them to that. But otherwise, their performance characteristics shouldn't be all that different. Anything else?
Uwe Ricken is typing, and I think Uwe is probably going to say...
No. It's okay. Don't worry about this. Wondering about the user table type. Does it mean that it's a table in the user database, or what does it mean? Yeah, you see, when I'm just referring to the question from Alexander, a user table type.
Yes.
Does it mean that it's in the user database, or so I didn't understand the question right?
For my examples here, yes, I'm creating types. I'm creating table
Yeah, that is
types
yeah.
in the AdventureWorks 2014 database.
Yes.
Yes.
Now I know what he meant. Yes. Okay, fine. Yeah, thank you.
Okay. All the numbers that I'm giving in this, and I'm talking about however many executions and however many milliseconds, all of this is just information that we got from Query Store, which we aggregated across a bunch of databases. So for what we're going to do later, I'm going to go ahead and turn on Query Store in this database. And now let's go back to the slides for a minute. All right. So my first thing was looking at the index view and trying to decide if the view was necessary or not. So this is requiring the Tablespoon operator. There seems to be a lot of work going on to update the indexed view. And like I said, the DML operators are more expensive than the normal kind of seek operators in the execution plan. So it seems like this is there's a lot going on in this stored procedure. So I looked at the view and what we're using for, and we refer to this a number of times in our code base. We refer to this view a lot, but why is it indexed? It's indexed because of aggregation. So a given item, I would figure most of the items in our system are probably present in a handful of distribution centers. What the view does is it gives us one row for that item, giving us its quantity numbers. This seemed like a lot of work to go through within this stored procedure, just to give us one row instead of looking at 3 or 4 rows. And I didn't really have a frame of reference for how expensive this was or how much time we would save by removing the index on this view. But I did remove the index on this view, and we got back about 20% of the total runtime for the stored procedure. So mainly the update statement got less expensive and had less work to do because we didn't have the indexed view anymore. And what the exact number was depended on what day you measured it from and to, but I would say around 20% of our runtime was reduced just from that change. Next, I had an idea that maybe our memory optimized table variables were part of the problem. Because table variables don't have statistics, is that lack of statistics leading us to a bad execution plan? Would we go down a better path if we did have, if we were using temp tables that do have statistics? Because the SQL Server always assumes that we're going to be returning one row from a table variable. So I tried this out and it was a terrible idea. The problem we ran into when we went back to using temp tables was Tempdb contention. And there's blog posts for weeks about Tempdb contention and how if you need to use this trace flag, or you need to add additional files in your Tempdb database and stuff like this to address the contention. And those might be effective, but not when you have hundreds of millions of executions per day. And the other thing is this: we weren't just creating one temp table for each execution of this procedure. We were creating like 3 internally. So creating that many, the thing that I think doesn't get stated enough in all of the blog posts about Tempdb contention is the other way to address it is to create fewer objects in Tempdb. That's the fundamental problem, is you're running into a bottleneck because you're creating so many objects so quickly in Tempdb. And in our case, with this many executions and that many temp tables, it just didn't work. This caused the stored procedure to take longer to run, and we reverted this change. So to me, it just made me like memory optimized table variables a lot more. They are pretty hard to beat. And I would say this, my goal was kind of a shot in the dark here to see if we would get a better execution plan, and that did not work. If however, you have a specific idea about what you think a good execution plan would look like, you'd be better off in my book to say, hey, I want it to be joining in this specific order and try to set the order, or to say, I want it to be using a specific index and to use an index hint. I would be more likely to go down that than to just hope that the temp table is going to do something better for me. So we reverted this change and we moved on from there. So unnecessary inserts. Like I said, if a row doesn't exist, we can't update it, and so then we're going to need to insert it. But logically, you're going to insert a row once and you're going to update it many, many, many times. And I actually ran some queries in our database to try and get an idea of how often we update things versus how often we insert them. And it seemed like we updated a couple hundred times each record. Adding into this, if we insert 0 rows in our insert statement, we're still going to run that trigger that I mentioned earlier. But the logic here seemed pretty simple to be able to skip our insert statement. If we know that our TVP is passing in 5 rows, and when we run our update statement, we update 5 rows, we don't need to insert anything. So we added a little flow control and we skipped the insert statement when our row counts matched. And we went from running the insert statement 350 million times to 6 million times, which was kind of about what I had expected at that point, but it was really pleasing to see that. What was surprising here is it didn't make much difference in how long our stored procedure ran. It went from 1.95 milliseconds to 1.91 milliseconds at this point. Still, with all the executions, this was 14,000 seconds of runtime per day, and actually another 16,000 from avoiding trigger executions. And the gist of why this was such a small amount of time is our insert statement was actually filtering out rows really effectively. And so there were basically no rows hitting the insert operator itself, the actual DML operator. So there was never a point that we were really trying to write anything the vast majority of these calls. Still, this is a small improvement, but it was an improvement. So we kept it and we moved forward. So now we go back to looking at the execution plan for our update statement itself. So there's several things going on here, and in the stored procedure, we actually had 2 different update statements. They're very similar, but we run either one or the other based on the parameters that are passed in. Slightly different math between the 2. I noticed we have a common table expression in the update statement, and it refers to the listings query we do earlier. We look to see if there are any listings, anything that's already for sale on a given item. Well, when we run that query, we kind of aggregate the numbers to get to know how many of that item are for sale. We add up, any of the listings, and we come out with one number. Well, we also added up those numbers, like we aggregated them again within the common table expression, which didn't make any sense. So we eliminated that. That was pretty easy to do. We have a second common table expression where we're doing a query against the base table. And we've got some case logic in the common table expression, but then in the main body of the query, we're joining to the CTE and joining to the underlying table again. This is why we're doing 2 index seeks. We're referencing the base table in the update, but also in the common table expression. And in both places, we have case logic to determine what the quantity should be based on the parameters. And it didn't make sense to me that we were doing it that way, but it made sense that why we had a second index seek. So part of what I did was I simplified, I kind of unified the case logic from the common table expression and the update. So we just had one case statement for each, for the quantity update. And that allowed us to get rid of the second common table expression. So there were 3 references against the table, the 2 index seeks and a key lookup. I always like eliminating key lookups whenever I can, especially if it's something I'm really trying to optimize. And what I found was, I was like, why are we using this other index and then doing a key lookup rather than using the clustered primary key? And what I found was the start of both indexes were the same. We had the index we were using has an account ID, an item ID, and the distribution center. But the primary key had the account ID, the item ID, and the distribution center. And they diverged after that, but it seemed like it would work just as well for us to use the primary key originally and then not have to do a key lookup as to use this non-clustered index. So I actually put a hint in the statement to use the primary key because we were going to be getting, we're only going to be looking at a handful of rows to begin with. These simplifications and eliminations of extra hits against the table reduced our runtime for the store procedure by 28%. This gave us back a little more than half a millisecond per execution, or 189,000 seconds per day. Now, let me flip over to Management Studio, and I regret having to work through optimized plans and examples, but this is kind of an example of what I was looking at in my stored procedure. So here's a statement against the sales order detail table. And in this update, I'm using a common table expression. And my common table expression is doing case logic for the product ID and the order quantity and the unit price. And I'm joining between the sales order table and the updates table variable. So this is basically presenting a result set that's then being used by the rest of the update statement. So I'm joining from the common table expression to the table again, and then doing additional case logic. This is basically the state the update was in when I found it. And what I did was I just rewrote the case logic so that it was setting the quantity variable like this, and we didn't need the common table expression anymore. And the advantage there is we're no longer hitting this table a second time, just to try to solidify that example a bit more. So this is what our execution plan looked like by getting rid of the common table expressions, simplifying the case logic, and getting rid of the extra, the key lookup. This is a lot smoother. And like I said earlier, I mentioned that the update operator, I'd expect the update operator to be a larger percentage of the cost of the execution plan. Well, we've done that. We've got it down. We've got it up to 73% now. And so many fewer operations. I really liked getting the execution plan to this point. So at this point, we had reduced the runtime of the procedure from 3.1 milliseconds to 1.4. But we had an additional idea. In the same way that we got rid of unnecessary insert statements, could we get rid of unnecessary updates? So a lot of the activity that goes on from updates, updating quantity, is being driven by our customers, and they're uploading files to us. They're working through the API and giving us updates, but it's all automated, and it's all. And we expect at least some of this is redundant, that people are uploading the same information to us multiple times. Set the quantity of this thing to 20. Set this thing to 20. 15 minutes later, we get another file, we get another API update. How many of these are unnecessary? We don't really know, but we suspect this from other parts of our system, that a lot of the activity that's going on is redundant. So what if we limited the updates to when the quantity is actually different? What if we took our update statement and just put a clause like this? We're going to run this update statement and change these values, but only where the old quantity is not equal to the new quantity. It seemed like a wonderful idea, but this actually caused our stored procedure to take longer to run, and the reason was the Halloween problem that I alluded to earlier. Now, the Halloween problem, like I said, was discovered in the 70s on a completely different database system. And all database systems have to kind of account for this. And what the problem is with the Halloween problem is if you are trying to update a value, if you're trying to update a specific column in your query, that is also one of the things you are querying and filtering on, then you can get into a circumstance where if you are operating in a row by row fashion, you can update a row, which means that row has to be moved from one page to another page. As you continue operating, going through whatever index you're using, you might hit that same row a second time based on whatever your where is, at which point you might update that row a second time. It makes more sense as an example to think of it for an update statement. But this can affect any DML statement. You can run into the Halloween problem on an insert, an update, a merge, a delete. And the gist of it, again, is to don't try to change the thing that you're querying. And what I just wrote was a prime example. We're updating the quantity, but we have the quantity in our where clause. So, and my hat's off. Kevin Fiesel actually presented a couple of weeks ago. When I ran into the problem I was seeing at that point, I asked for his advice, and he looked at the problem and said, "This sounds like the Halloween problem to me," and he was dead on. I think I had read about this years before, but I had never actually seen it. So the Halloween problem is us updating the same row multiple times. But SQL Server knows that that can happen, and it prevented that from happening. It prevented this by putting blocking operators into my execution plan. So now instead of everything flowing from one operator to the next, one row at a time, going from this index through this join operator to the next table, instead of it flowing on a row by row basis, we had a big, I think we had a table spool operator, an eager spool operator that was causing us to wait until all of the rows had been queried and everything had been joined together before we passed that information on. And these blocking operators are not great. Actually, I think the first thing I blogged on, and I have a link here, was actually a blog about blocking operators and what they are. And the reason I blogged on that was I had been working with SQL Server, I think at 15 years at that point, and I had never actually heard the term of blocking operators. So I found it fascinating when I came across that. And the gist is, this is really bad for performance. This caused our stored procedure to take like significantly like 50% more runtime. So this was another change that we had to roll back, that where clause that we had added to our update statement. But we didn't want to accept defeat on that one, and we came up with another idea. The reason there is a blocking operator in my execution plan is this: SQL Server is really trying to change the select side of our statement from the data changing. So the select part and the update part, it kind of wants to separate the two of those. It wants to run the select, get all of the rows, have all of the rows in one place at one time, and then say, okay, let's update this list of rows. So my thought was, why don't we just actually why don't we completely separate the two operations? What if I queried all the data we want into a temp table? Well, that would be terrible because temp tables running hundreds of millions of times. No, we'll put them into a memory optimized table variable. We will do all the math, put it into our table variable finished with the new quantity and the old quantity for each row. Now, we'll need to run a statement that checks the results and sees what's in our memory optimized table variable. If none of those rows show that the quantity is changing, then we don't need to run the update statement at all. This also required us to change the insert logic, because our insert was based on row counts, and if we're not actually updating any rows, then we would need to change it as well. So we have a similar query for our insert statement that's based on a left join instead of just using the row counts. And I have an example I'll run through in a minute to show you what a similar operation in the test database would look like. Part of my concern here was how much overhead this was going to take. So we went from doing an update statement to doing a select statement and an update statement with another statement that is going to check the results of our memory optimized table variable. And I didn't have a frame of reference for how long those other operations would take. And I was very surprised with the results. So running a query against the underlying physical table and the memory optimized table variable, and inserting those results into a new memory optimized table variable took between 90 and 100 microseconds. Checking the results took another 10 to 20 microseconds. The result was we were able to skip the update statement 96% of the time. We didn't even run the statement. Because it was just going to be unnecessary. We weren't actually changing any of the quantity values. This got the average duration of our stored procedure down to 320 microseconds. So by simply not running the redundant information and coming up with an efficient way to do so saved us a gigantic amount of time, which calls for a victory dance, in my opinion. So let me go back to Management Studio. So I had set up a memory optimized table type, turned on query store, And here's the example that I want to go through. This is a similar stored procedure that I wrote against the AdventureWorks database. So what I'm doing here is doing a simple query to set the order status. I'm passing in a TVP, our memory optimized TVPs, to our stored procedure that's going to provide what updates I want to make. And similar to my stored procedure, we had a couple of update statements here. I've got a couple here. Either we're going to be changing the quantity relatively, or we're going to be doing an absolute update. If it's relative, we're going to be, if it's relative, we're going to be looking at the table variable and the underlying table. And we're going to set the order quantity equal to what is in the TVP. We're going to be updating the unit price, and we're going to be updating the modified date. If it's an absolute update, we're going to be updating the underlying table based on the TVP. But if something is in the physical table, is in sales order detail, but not in our TVP, then we're going to delete that out of the table, just as a little twist. And afterwards, we have an insert statement here that we are going to try to insert anything that's in the TVP into the table as long as the record in the table does not exist. So this is our first stored procedure, and here is the second. The second is doing the same thing that I did, where we select the data from the TVP and the underlying table and push it into a new table variable. So here, we're only going to run the update statement if we pass this check. So if the order quantity changes or the unit price changes for any of the rows in that table, then we run our update statement. Otherwise, nothing changed and we don't need to run the update. I do similar logic down here for our absolute change. So we're again populating our table variable. If there's no changes, we don't run the update. Here, we're checking detail changes, and we look to see if there is a new value for each record, meaning they're in the TVP. If the record is not in the TVP, then we don't want it to be in the underlying table anymore, in which case we run the delete. But if there's no records in the table variable where the new values are null, then we don't run the delete statement. And after our updates and our deletes, we check to see if the current value is null anywhere. If the current value is null, then that means it's not in the underlying table, but it is in the TVP, in which case we want to insert it. But if we don't see that null, we don't insert it. So let me run this. And did I actually create the other table? Okay, we created the other procedure. Now, here's what I'm going to do. I'm actually going to make sure I haven't changed the logic here. Great. I'm going to run a query and look for a specific sales order from the underlying table. I'm going to query that information out and put it into a table variable. And I'm going to try to run the first stored procedure and see my results. And then I'm going to run the second procedure. And let's see. I'm going to do this multiple times just so we can get, just to try to alleviate any cold cache issues of running this query for the first time. And we're going to look at the results. So how long did it take us to do this in Query Store? So here we've got the original version of the stored procedure, SP_detail update. We've got a delete statement, we've got a select, we've got an insert, we've got an update. And the average duration is 85 microseconds. Of course, these numbers are all in microseconds in Query Store. This update statement is taking 31 milliseconds. Now, I definitely run into some cold cache issues with this, and if I was to keep running the statement, we would probably see this coming down. Probably the first operation is just getting things in cache. But look at what we see when I look at the second stored procedure. Whoop. The updated stored procedure, I can see we have an insert statement we're inserting into the table variable. And then we have an if exists statement, an if exists, and if exists, and a select statement. These if exists are us doing checks to see if it's necessary for us to do an insert, an update, or a delete. In all cases, we're doing these operations in 10 microseconds here, 17 here, 10 here. The insert to populate the table variable, which is an extra statement that we added to this, takes 100 milliseconds, 100 microseconds. But it's saving us a ton of time in the long run because we aren't running any of our actual DML statements. Any questions so far? We'll be wrapping up in just another minute.
James is asking if one of the columns is null currently and also null in the updated data, wouldn't that prompt a not needed update? Could it be changed to an accept check instead?
Yes, and it's going to depend. It's going to depend on your exact circumstance on whether the data can be null in any of those fields. In my case, we're populating those records. Let me see. In the table variable for each of those calls, none of those fields should be null in the TVP, and I believe none of them should be null in the sales order detail table. If your table is different or if your TVP is different, then you might need to negotiate the logic a little bit. But yeah, that's a good point. In our case, and let's see, and some of these are going to be slightly different too, like how you're populating it. In this case, I'm actually joining between the two, and I'm doing a full join if it was the possibility that I might want to delete something, expecting that the record is in the underlying table but not in the TVP. So you might have to adjust this multiple ways. If I'm only anticipating doing updates, I'm doing a left join. So there's going to be some changes to the logic depending on your particulars. But yeah, this was written knowing how the nullability is of the underlying table and the TVP. Anything else?
No, nothing more. I have one actually. I mean, I know there are problems with the merge statement, but yeah. Did you try solving it with the merge statement? And
I did not. I really like merge statements as kind of a logical construct or as a coding construct. I like how it looks to write code with a merge statement, but I don't like the performance characteristics, and I don't feel like I'm as good at tweaking a merge statement as I am with the others. So, and I know there's entire blog posts just on all the fixes and changes within the SQL Server, within SQL Server itself for merge statements. And I'm not entirely up on those. I know that I've used them at times, and I've kind of gone away from using them. It doesn't seem like it performs the way I would like, or either that, or I'm not as confident that I can tweak it as much as I could tweak a simple update statement.
Cool.
So, and if let me do one more thing real quick. So I had mentioned, if I run this more times, that I start to see the numbers coming down for the update statement. And let me see, if I run this a few more times now, I want to see it. Yeah, this is saying my update statement is down to like 5.6 milliseconds. So that's a lot less than it was originally, but it's still a lot slower than we're getting from our optimized version of this using the memory optimized TVP and skipping the update statements. So I did want to do one more thing. Pardon me. I went back and did a little algebra because I just kind of wanted to double check. And what is our break-even point? So my concern initially was with doing this that we were adding extra overhead to the statement by having to populate the table variable and then do checks against the table variable. I ran this a bunch of times. I run my example a bunch of times against the AdventureWorks 2014 database to see at what point the update would get to. And at one point, I think I ran this 100 or more times, and the update had averaged out to about 2 milliseconds. But the queries against the memory optimized table were taking like 70, and that's between populating the table variable and then reading it later. And so the gist of this is if you skip the update operation 3.5% of the time, then we've broken even, and the overhead we've gotten has been canceled out by the number of times we don't run the update statement. So if I skip running the update statement 4% of the time, I'm actually gaining time. And that depends on the particulars of my numbers. And these are the numbers I've got on my system where I, this is my home system. I typically, run Steam games on this system. So this is not a production SQL Server, but this is also a lot of the work here is going on inside memory. So it's not like we're writing to physical storage for the table variable part of this. I have a number of references in this slide deck. So I have a blog post or two on the Halloween problem. I found it fascinating when I ran across it. And I put in some information to describe the thing. But Paul White had a series of blog posts from like 2013 that are more like a master's thesis on the Halloween problem. I was not trying to rewrite that. So if you want more information on the Halloween problem, definitely go look at Paul White's stuff. He has a wealth of detail and some really good examples for that. Aaron Bertrand has had a really good blog post on upsert coding patterns, and he had some very specific recommendations about like hints and stuff that I was not aware of. So if that is a thing that you have to write, if you have to write upsert statements, you might want to go check that out. I have blogs on the Halloween problem. I have blogs on blocking operators, and I have blogs on that I had updated multiple times as we went through updating this stored procedure. And like I said, this was work that went over course of a couple of months in the early pandemic. And each change we did in isolation, which I think was a fantastic idea in this case, because some of our ideas worked out really well and some of our ideas different. If we had released them all at one time, it would have been really difficult to separate them all out and figure out what was working and what wasn't. I've also got links to TVPs and memory optimized table variables. If they're not a thing you use, you might want to look up on them. I use these constantly at work. And a couple more GitHub links. So I've got a link in here for the Qds Toolbox. This was released by a couple of my coworkers from ChannelAdvisor. And what the Qds Toolbox is it's some tools for using Query Store, especially if you're not really used to using Query Store. You can use the Qds Toolbox and set up some reports and have a lot of the work already done for you and kind of ease your way into using Query Store. I've done several blogs this year about the Qds Toolbox, and there's still parts of it I need to blog about. So stay tuned on that. And my presentation slides and examples are in my deck here, but you would need to download it to actually have that link. So my GitHub page should be github.com/SQLJared, and you can go there to download my slides and examples if you are interested. Oh.
I already posted the link to the every millisecond counts repository and also the Qds Toolbox repository on GitHub.
Thank you very much. And if you have any questions, feel free to @me, and I will try to respond when I have the chance.
Cool. Thanks, Jared. I really like that it is an actual case study and that you went through the different things that didn't work out so well as well. So
yeah, that's part of the work too.
It is. I mean, it's just as important in optimizations. Don't try this; it won't work anyway. So. At least in this scenario.
Yes, don't create temp tables in something you run hundreds of millions of times a day. It's a bad idea.
Yeah, true. When you deployed your changes, did you use a canary deploy or something? So you just picked one server to deploy the changes to, or?
At times we do, and some of the information, like we use Query Store, and in production, we aggregate the information from all of our databases because we have hundreds of databases, and Query Store really only exists within the database. You can't even look at it, across the instance. We do canary deploys sometimes. I don't know if we did canary deploys on either of these, but there are other times when if we are more concerned about a thing, we might use canary deploys. We did not in this case that I recall. And one of the things too is, while we aggregate the data from Query Store in production, we don't have kind of the same system in place for development. So I think that did make it a little harder to see where we were having problems on the things that were causing performance problems. We didn't really observe that in the lowers, but it's also a matter of we don't run the statements nearly as often in our development environments as we do in production.
Yeah, I mean that's what I think is the hardest to spot, like blocking issues when you're running your tests, because it's very hard to simulate a real production workload. So,
it is. Even
if there are tools like the SQL, I don't remember the name, Gianluca Sartori has
SQL Stress or?
No, I think it's SQL Workload or something that Gianluca has written, and it's also available if you look for Spaghetti DBA's repository on GitHub. It's going to be.
I hadn't heard of that one specifically, but I'm always looking for good tools to test stuff.
Yeah, but I think they are. I mean, if you want to run 1 day worth of production workload and really test if your changes make any, if they cause any blocking, well, you have to let it run for 1 day, and running at the same time. So all the statements has to be. Otherwise, you won't see if you have blocking. If you run them on 2 threads, well, then you won't have the same blocking as if you have 200 threads running simultaneously. So it's hard. On the other hand, I think if we do like you did with memory optimized table variables, well, we don't need to think so much about blocking in those, at least.
Yeah, that's a big thing too. It's just the fact that we don't have the Tempdb contention is a huge benefit from those. That's a thing that we run into a lot in our environment. Anyways, like page latch contention in general is kind of the thing where we run into a lot of things. We don't see a lot of blocking issues, but we do see a lot of page latch contention level issues.
Mm-hmm. Yeah, and I mean a physical storage is only going to be so fast, and your RAM is going to be faster. You really can't. Even with SSDs and all the cool stuff, the RAM is going to be faster.
Yeah, I was completely amazed to see the numbers going down into the microseconds.
Yeah, and especially when you use like table valued parameters, where I mean they're schema only. You don't have anything that's written anywhere outside of the RAM.
Right.
And as far as I could see or understand from your presentation, you don't have a huge amount of data in those memory optimized table variables, right?
No, and I think at the example in the actual procedure, I think the TVP that was passing in information to the procedure probably only had a handful of columns. It's not a very wide table underneath it, but I think the TVP was basically giving us, the identifier for the item, how much quantity in which distribution center. I mean, there's no reason to have anything additional. So.
No, so I know some people are a bit afraid of using memory optimized because they don't know how much memory it will consume.
Right.
In this case, it can't really be that much. So.
Yeah, the typical case, like I said, you probably have for a given item, you probably only have it in 2 to 5 distribution centers. But that is a valid point. That's a really good point. So what were we putting in there? We were putting in, a couple of integers. It was probably like the table variable probably has 3 or 4 integers. So, well, how large is that? 4 integers is 16 kilobytes, right? Well, how many rows are you likely going to have? Well, you can. So if you estimate it out, you can figure out how much space that should be taking up for the TVP, how much that should be in memory. You can limit the number of rows depending on what you're doing. Maybe you limit the number of the code should have something in it explicit to limit the number of rows of data you're going to be putting in a TVP. And if you're putting in text strings, of course, that's going to be a lot larger than passing in numerical values. But if you're putting in text strings, especially in the large, maybe you don't call it with 100 rows in your TVP. Maybe you run it with 10 rows in your TVP. You're still reducing the number of calls to a stored procedure, and you're still reducing your round trips. But you can estimate how much you can come up with a reasonable number for how much memory is going to be taken up by a given call. And then, of course, you need to think about the fact, well, we're probably calling this stored procedure more than once at a time, right? So all those questions are very fair to ask. And I know we've had a discussion or two because we do use memory optimized TVPs a lot. And one of my coworkers was working on one where she was running a TVP that had, I think, more data being passed in, and a lot of it was text string stuff. And she was finding that, it was actually faster to run it with 10 rows at a time than with 50, but also much smaller memory allocations. So that was part of the performance difference.
Yeah. Cool. So I guess for you, it's time for breakfast or something.
It is very early on the East Coast. It is still dark over here.
Yeah, I didn't say that initially. So if anyone asked what I'm talking about, Jared is on the East Coast of the US. So when I say that SQL Friday starts at noon, it doesn't for all the speakers.
I'm fairly certain when I saw this, I saw that it was in European time, but maybe I didn't realize it was in Central European time.
No, I guess if it would have been,
I think I was thinking
London would have given you an hour or something.
Yeah. Okay. I was thinking maybe I thought it was going to be at like 8 a.m., not at like 6 a.m. But I'm very glad you let me come on and talk, and I hope that you have a very good day.
And you, and well, soon it's Christmas. So like I said initially, it was the last SQL Friday of the season. I think it was a brilliant way to end the season. So thank you so much for that, Jared. And to both you and everyone else, have nice holidays, and whatever you celebrate, Christmas or something else, just have a brilliant weekend.